Alright, so we have the following super cool group theory statement that if G is a group and if the order of G equals P is a prime number, then G is a cyclic group. This is part of a family of beautiful statements. The deeper and deeper you go into finite group theory, you find lots and lots of statements where just knowing what the order of the group is can tell you everything about the group or a whole lot about the group through some clever reasoning. And this is the first example of that. And we're going to walk through what the proof is here, and it's really beautiful. Now here's a hack. If you see this as an exercise in a textbook or in a class, then if you know what you're trying to prove, you can sort of get an idea for what the proof will look like. So to show that G is a cyclic group, what does that mean? It means that there is a generator. Okay, so what we're looking for is we're looking for some element G in G. Okay, so want to find an element, want to find G in G such that the cyclic subgroup generated by G. Okay, so all the powers of G. Okay, so sometimes this is denoted in this notation. This is the set of all powers of G, G power I, so that I is in Z. Okay, we want to show that this set of powers of G, which is a subgroup of G, because the product of two powers of G is again a power of G, we want to show that this is equal to G. Okay, that's a way of phrasing what we want to prove. In other words, we want to prove that every element of the group is a power of G. Okay, so how do we find such a G? So the first thing we should think about again is if we have an element of G, what do we need it to satisfy to be a generator of the group, right? What do we need it to satisfy? Now, here's the cool trick, okay, and you may see this already. Now, first of all, the identity element will not do. The identity element generates its own subgroup. It's just itself, okay? It's a trivial subgroup, okay? So if you try to take the identity E of G, you'll just get E. Just get the singleton set consisting of E. So you have to choose a G that's not the identity, okay? So that's an important part of the proof. So let's start off with the proof. So let's choose a G. So let G not equal to E, okay, be an element of G. Now, we don't know yet that G is going to generate the group, but we're almost there because what we need to show is that this thing is a subgroup of G, and we're going to use a fundamental group theory theorem called Lagrange's theorem. So we know that this is a subgroup of G. That's an exercise because the product of any two powers of G is again a power of G, and the inverse of a power of G is also a power of G. It's G power I inverse is G power negative I. Okay, so and G power negative I, if I is positive, is just the product of G inverse I times. Okay, so that's what it means to take G power negative I in a group. And so in that situation, we know that this is a subgroup of G. And because we know that G is prime order, we have to use that too. We're going to appeal to Lagrange's theorem. Okay, we know that this is a subgroup of G. So we know that G is a subgroup of G. And sometimes in group theory, we sort of know that when we use the subset notation, that's typically for sets. But in the context of groups, you can also say this means subgroup because in certain contexts, you only deal with subgroups, not even with subsets, in many contexts actually. But just for clarity, we write this. So G is a subgroup. Now Lagrange's theorem implies that the order of the subgroup has to divide the order of G. Okay, so Lagrange's theorem implies that the order of any subgroup, which is the number of elements in the subgroup, is a divisor of the order of the whole group. So therefore, we know Lagrange's theorem implies that the order of this subgroup is a divisor of P. But P is a prime number, that's where we use the prime condition. And we know that because G is not the identity, this is not the trivial subgroup. So therefore, we know that this has to be the whole group. Why does it have to be the whole group? Because it is a subset of G with cardinality equal to P. And so for sets, if you have two finite sets and they have the same cardinality and one's a subset of the other, then they have to be equal. So that implies that. So therefore, G is cyclic. In fact, every non-identity element is a generator of G. Okay, so that's number one. And I'm going to leave an exercise for you down in the comments below. Okay, I want you to comment. I read every comment and love reading them, and I will do my best to respond to everyone. I've so far responded to every comment on my channel. Okay, so except troll comments, I guess. So basically, suppose we instead change the statement. If G is a group with only two subgroups, prove that G has to be cyclic. That's my exercise to you. You can replay that again if you need to, and drop a comment down below with your solution. And I'm super excited to read that and see you in the next video. I'm a research mathematician. My area of research is very much in group theory. I do a lot of different things, but group theory is one of them. And what better way to learn group theory? So check out my channel for a playlist on all my videos on group theory, which is growing. And another video you're going to love on my channel. My channel has everything, all levels of math, all topics. You're going to learn everything, including very advanced stuff eventually. So even if this stuff Standard 2, you're going to learn even more advanced stuff. So don't forget to subscribe and like, share with friends, and I'm super excited to see you in the next video.